In this video, we keep on presenting simplifications that preserve the language. Our goal now is to erase all unary rules, that is, all of the form variable rewrites into variable. We'll use the example from previous lecture about removal of lambda productions. Note that this grammar has three unary rules. It is not enough to just erase the unary rules if you want to preserve the generated language. In a first step, we'll compute which variables are reachable from others using only unary rules. We define this set for a variable x as the set of variables that are reachable from x using unary rules from the grammar. These sets can be computed by the following algorithm. In a first step, we say that every variable can reach itself, in fact in 0 rewriting steps. After that, in the loop, we'll keep on computing other variables reachable in more than 0 steps. If a variable z, at the moment not detected as reachable from x, is reachable in one step by a variable y reachable from x, then we add z as reachable from x. The algorithm halts when no new information is detected. Let's see how the algorithm performs in our example. This is our grammar, and this will be the result of the execution of the algorithm. In a first step, each variable is marked as reachable from itself. Then, since there is a rule from S to A and S is reachable from S, then we add A to the set of reachable variables from S. Similarly, we add B to the set of reachable variables from S. Next, since there is a rule going from S' to S and S' is reachable from S', we add S to the reachables from S'. Finally, since there are rules going from S to A and B, and S has been detected as reachable from S', we add A and B as reachable from S'. At the moment, no more information can be inferred, and the execution of the algorithm ends. The proof of the fact that the algorithm computes for each variable all the variables that are reachable using only unary rules is very similar to the proof that we present for the algorithm computing the set of nullable symbols, and hence is left as exercise. Now we know that we can compute the set of variables reachable using only unary rules. We'll see now how to use this information to remove unary productions preserving the language. Let G be the grammar that we want to transform. The new G' and G will be equal except for the set of rules. The rules of G' will be of the form x rewrites to w, satisfying the following. W cannot be a variable, because otherwise we would have an unary production. Moreover, w has to be the right-hand side of a variable y in a rule of G, such that y is reachable using unary productions from x. In this way, if before x could reach y using unary productions and then be replaced by w, now it looks ahead and goes straight to w. It has to be done this way because now we don't have unary rules. Let's see in our example how unary rules can be removed. This is the grammar that we had, and this is the resulting grammar. Since S' could reach itself using unary rules, we add as right-hand sides of the new S' all right-hand sides that were right-hand sides of S' and that were not just a single variable. In this case, only lambda satisfies this condition, and we add it. Since S' could reach S with unary rules, we add as right-hand side of the new S' all right-hand sides of S that are not single variables. Only AB satisfies this condition. Similarly, we add A, B, B, and B as right-hand sides of S'. We also add A, B, and B as right-hand sides of S. The right-hand sides of A and B does not change, since both could only reach themselves using unary rules, and they did not have single variables in the right-hand side. Note that in the resulting grammar, symbol S is useless, since it is not reachable from the initial symbol S'. We want now to remove all symbols that cannot be used in any derivation from the initial symbol into a terminal word. This leads us to the next transformation: removal of non-useful symbols. We define a symbol as useful if it occurs in some derivation from the initial symbol into a terminal word. A useful symbol must be reachable and fruitful according to the following definitions. We define a symbol as reachable if it occurs in a derivation from the initial symbol. We define a symbol as fruitful if there exists a derivation from it into a terminal word. When all the symbols of a grammar are reachable and fruitful, then all of them are useful. When there is some symbol non-reachable or non-fruitful, things get complicated, since even though every useful symbol must be reachable and fruitful, there may be reachable and fruitful symbols that are non-useful. Let's see an example of all that. In this grammar, x is not useful because it is not reachable from the initial symbol. Y is not useful because it is not fruitful. Variable z is reachable by this rule, and it is also fruitful by this rule. However, it is not useful. Note that after applying this rule, z goes together with y, which is not fruitful. Hence, there will not exist any derivation containing z from s into a terminal word. In summary, even when z is reachable and fruitful, it is not useful because there are other reachable but not fruitful symbols that prevent it. If we proceed by first removing all non-reachable symbols and afterwards removing all the non-fruitful symbols of the resulting grammar, all the non-useful symbols may not be removed. This is because after erasing a non-fruitful symbol, as y, another one may become non-reachable, such as z. However, if we proceed by first erasing the non-fruitful and then the non-reachable of the resulting grammar, we get a grammar where all the symbols are useful. The proof of this fact is left as exercise. The calculation of the sets of reachable and fruitful symbols can be done with iterative fixed point algorithms, similar to the ones that we already saw. In the case of reachable symbols, we mark s as reachable at the beginning. And while we see an x that has not been detected as reachable yet, but can be reached from a symbol already detected as reachable, we add x as reachable. In the case of the fruitful symbols, where we see an x that has not been detected as fruitful yet, but can be rewritten into a concatenation of fruitful symbols and terminals, we add x as fruitful.